Welcome back. This is Dr. Roberts for Intro to Electrical and Computer Engineering at UTEP, Week 10, Fall 2021, and we're doing practice problems from our Tuesday lecture. Right, try to do it live. And practice problem 4, which you can see this is practice 4, right? 4, if I can write properly, asks us to analyze this circuit here, where we want to find V out over V in. What is the filter type, and what is the cutoff frequency if we have these values. Now, if you're just joining us for that, if you go back to practice problem 3, we just analyzed a very similar circuit where the only difference here is we swap the positions of the resistor and the capacitor. So we're going to follow the exact same process we did before and move from there, right? What do we do, right? We have this capacitor here. Whenever we see a capacitor, we should go in the phasor domain. If we do that, we can redraw. And I will redraw all my capacitors as resistors. Right, and this is V out. Now, a resistor in the time domain has the same value after returning to the frequency domain as a phasor. And a capacitor becomes 1 over j omega C2 in this case. Right. And now if we look at this, we're like, oh, okay, cool. We got two resistors in series. We want this voltage. We can use our voltage divider equation where we say, okay. So if we do that, we see that V out is going to be equal to then V in. And on top of our voltage divider equation is what we're measuring across. So we're actually measuring like across R2. So it's going to be R2. And on the bottom is the equivalent impedance, which will be these two in series. And we can write it either way, right? So we can write that as R2 plus 1 over j omega C2, or you could flip them around. It doesn't matter. And there is correct answer. However, this is kind of ugly. So what we can do then is let's take this whole thing and multiply through by j omega C2 over j omega C2 and clean up this fraction. So this will multiply on top and this will multiply on the bottom. And we can also divide this across at the same time. Right, I've kind of combined a few steps here. So we have that moved, and then that's going to be equal to j omega C2 R2, right, multiply in, and this one goes across and becomes j omega C2 R2 plus j omega C2 over j omega C2. This becomes 1, so it says that V out over V in is going to be equal j omega, and I'll just switch these two to R2 C2. It doesn't matter, but I think RC, so in my head, this makes me happy with my OCD. J2 R2 C2 plus 1. So there is part A. Right, notice now, like compared to the last one, we have frequency in the numerator and the denominator. So let's see what happens. For what filter type is this, right? And by inspection, if we look, we see on this particular circuit, we have a capacitor connecting the input to the output. So if the frequency is 0, right, if the frequency is 0, then this will become an open, right? No current will flow, so there's no connection input-output at low frequencies. If this frequency is infinite, then there's a lot of change. This will act like a wire. So this one will block low frequencies and will let high frequencies pass. So this is and there's no other energy. This is a passive high-pass filter. But let's analyze it mathematically using the transfer function here. So then I can ask you, so if basically omega is 0, right, we can plug that in, then we get that j times 0 R2 C2 over j 0 R2 C2 plus 1, which is equal to 0 over 0 plus 1, which is equal to 0 over 1, which is equal to 0. So that says that this circuit blocks low frequency. And similarly, if we do then omega is equal to infinity, we can plug it in, so we get that j times infinity R2 C2 over j infinity R2 C2 plus 1, which is equal to infinity over infinity plus 1, which is equal to infinity over infinity, which is equal to 1, right? So then that means it passes high frequency. So because of that, then part B tells this is a passive high pass filter. So that's part B. And then part C asks again, if you have these values, what is our cutoff frequency? We know that FC is equal to 1 over 2 pi RC in hertz, where the resistance has to be in ohms and the capacitance has to be in farads. So we can do that conversion. So we say that R, it's, or whatever, call them R1, R2, right? So I'm calling them R2 here. So this is find C2, R2, same thing. Our resistor values. So we get that R2 is going to be equal to, it's 100 kilo ohms. We want to convert that into ohms. You see the 100 kilo ohms here. Then we have 1 kilo ohm is 1,000 ohms. These cancel. So we see that R2 is equal to 100,000 ohms. And similarly, we see that C2 is equal to 1 microfarad, and we know that 1 microfarad becomes, right, 1 microfarad is 10 to the negative 6 farads, so that's equal to 10 to the negative 6 farads. If we do that, we can plug in our equation, and we see, okay, then the F sub C is equal to 1 over 2 pi times 100,000 times 10 to the negative 6, which is equal to 1.59 hertz. So there's part C. And similarly, I would challenge you to look at practice problem 3, and you could draw the Bode plot, right? You would flip it with respect to the high pass, with the cutoff frequency, right? So it's going to be blocking low frequencies, and it'll be flat at high frequencies. So that's practice problem 4, and I will see you in the next problem.